It's like weird how you're.
Okay.
Yeah.
She's like, oh, my thing helped with that. I know I'm seeing it. I do take it.
It's like half year.
Today I want to focus on these very specific type of FRQ problems. These are called kind of rate in, rate out problems. So we'll spend today on that. The first quiz is not going to be over this topic, but I do want to introduce this early so that we can kind of have time to kind of process these type of problems so that by the time we get to reviewing it again after this first quiz, then it'll be more familiar. So, but I wanted to introduce this early since we haven't quite seen these types of problems yet. So, quiz is tomorrow. Area and volume quiz. Again, I encourage you guys to work through pages 11 through 13, and then also pages 1 through 4 if you haven't finished that already. Oh, sorry, I also come around and check your homework. So. So 1 through 7, the back of your packets. Yes.
I just feel like.
Oh.
So bad. I mean, you meet random people telling me, this is always sweet and stuff. Oh, guys, it was the sweet and sour certificate from China restaurant. It was. I mean, that was fun. No, it was like a week before. Yes.
So I just.
Yeah, I was so happy with the word. Oh my God. I was like, I did it for like 5 years. Only thing Washington State. We have a new buzzer. We have to train it.
Yeah.
No. We're all gonna. I was wearing it was probably different. So. I mean, where's the word question? On every single method. I added the top. And I made the this is the Levi House, a lot of this is 8.4. This is 8.4. From this, I believe that's
it.
I'm not. I used.
But yes. We should be.
I just woke up. Well, it's more like Lions National Park, like fight. Let's say I accept and then I put a smile face. Yes, it is. I literally was like, it was too late at night. I was basically, I had to respond to the email. I was trying to be like,
I accept this generous offer. Thank you so much for choosing me to be player.
Yeah.
It was Friday.
I was like, I'm like gonna look at it and be like, oh, okay, check for it. Yeah, but let's select. Right today.
It's becoming a lot of.
Oh, wait, what's been after we know, y'all. Our project is gonna be on. What? Am I? I am. No, I'm gonna do it on the environmental effects of these. No, scholar.
All right, guys, we're on page 1. Okay. Hey, let me go through some concept reminders before we. Oh, and then we're gonna need our calculator for this. Okay. So concept reminders. If velocity is meters per second, then we know v prime is going to be acceleration will be meters per second squared. So anytime we do a derivative or integral, we expect our units to change. Okay? We're applying a derivative, which is the rate of a change of the starting function. And it should make sense, right? If I do change in velocity over change in time, I'm getting meters per second, which is meters per second squared. Okay. Likewise, if velocity is meters per second, then the integral of velocity will change to a new unit in terms of meters, right? And the reason why is because we're accumulating that rate. We're finding the area under the graph through integration, which will result in a new unit of measure. So that v of t is meters per second, that dt is time. So if I multiply meters per second times second, I'm going to be back up to meters, right? So here, example, if I travel 60 miles per hour over a 5-hour period, 60 miles per hour times 5 hours will be 300 miles. And then the way we can write it in integral notation is the integral from 0 to 5 of 60 is equal to 300, right? And that 60 and dt will multiply out to be, turn out to be miles. Okay. So it's the same idea here that every time we take the integral, we're going to make our units rise to a different, out of the rate unit. Okay. So let's look at number 1 here. It says the rate at which people enter an amusement park on a given day is modeled by the function e of t, defined by this 15,600 over t squared minus 24t plus 160. The rate at which people leave an amusement park on the same day is modeled by L, which is defined by L of t. Right? Both E of t and L of t are measured in people per hour. So that's important here, right? That this is not going to give us the number of people at any time, at any moment in time. It's going to give us the rate of people are entering or leaving the park at that hour. Measured in hours after midnight, these functions are valid between 9 and 23. So that means the park opens at 9 a.m. and it closes at 11 p.m. Okay, but this is in military time here. At time t equals 9, there are no people in the park. So how many people have entered the park by 5 p.m.? So the only function we need is what?
Entry.
Yeah, entry, this E of t, right? So if we want to find out the total number of people who've entered in the park, what can we do?
Integral.
Yeah, the integral, right? So we do the integral
from 9 to 17. We're going to accumulate all the rates together. And this people per hour is going to turn into number of people. I'm sorry. Yep. So we're going to use our calculator here. And we don't have to show our work, right? You just set up the integral and make the calculator do all the work for you. Let's go ahead and do this because we're going to need to use E of t and L of t multiple times. So let's just have y1 hold that E of t function. So if we do alpha trace, sorry, that's not alpha y equals, can get that n over d, that math print feature to show up, and then go ahead and start entering your function. Always use variable x, even if even on paper, even if paper shows you a different variable, never do another variable besides x. Okay, math 9. Alpha trace, I'll choose y1, dx. Okay, so if I round to the closest whole number, around 6,004 people have entered the park between 9 and 5 p.m. Okay. Part B, the price of admission to the park is $15 until 5 p.m. After 5, though, the price of admission drops to $11. How much is collected from admissions to the park on the given day? Round your answer to the nearest whole number. So we basically have to figure out how many people do we charge $15 and how many people do we charge $11. So how can we set this up? Good. And then once we find the number of people, we can multiply them by the appropriate amount, right? So we already know this is 6,004 people. We can multiply that by 15, and then we can adjust our integral, figure out how many people do we charge $11. I think anything in that range, it really depends on where you round it to. So let me see. Okay. So I think if we're in that, anything in that range, I think is fine. Okay, part C. Let h of t be equal to the integral from 9 to t of e of x minus L of x. Okay. The value of h of 17, the nearest whole number is 3725. Find the value of h prime of 17. And then explain the meaning of h of 17 and h prime of 17 in the context of this problem here. So hold on. And spell out a few things here. So we know what h of t is equal to. Let me write this out. So that means h of 17 must be equal to this. And if I break this down even further, h of 17 is this, right? So what does this represent? Yeah, number of people who've entered in the park. What does the integral from 9 to 17 of L of x give us? Yeah, the number of people who've left. So what do you think if I subtract these two numbers, what am I going to get in return? Left in the park, right? So that means this is going to tell us how many people are left in the park at 5 p.m. So we know that h of 17 is 3725. So we know what that means now. That must mean people left in the park.
You don't have to show where it takes place.
Nope, you don't. I just want to kind of show you all the breakdowns so that it's very clear. So let's talk about h prime of 17. So before we do that, though, let me break down what h prime of t is, right? H prime of t then must mean the derivative of this integral notation. Right. If h of t is the integral from 9 to t of e of x minus L of x, then h prime of t must be the derivative of that. And what does this remind you of?
Fundamental theorem of calculus.
Yeah, second, right? Second theorem says, okay, I can just wipe these two out. They're going to undo each other. The upper bound gets inserted in. So h prime is really just e of t minus L of t. So then, therefore, h prime of 17 must mean e of 17 minus L of 17. Right? Everybody following so far? So we can just enter that in the calculator, right? I'm going to have y2 hold my L of t function. I'm going to just go ahead and enter that. I'm going to have to call that a couple of times here. So I'm going to let my y of 2 be that 9890 divided by t squared minus 38t plus 370. I'm going to go ahead and enter that in the calculator. gonna get a decimal value out of it here. So the I have here negative 380.281.
No fraction.
Yeah, let's do a decimal value to three places here. Now, what is that? What's the unit going to be here? H of t is H of t is going to be the integral of v of x, right? And so h prime is still going to be what? People per hour, right? So what is that negative 380 people per hour? What does that tell us?
How many people are leaving the park
And
per hour?
Yeah, or so we can also say, I think you guys have it, but I can also say the number of people in the park is decreasing by that rate, right? Or shrinking by this rate. Okay, so we know E of t is the rate at which people are entering the park. L of t is the rate at which people are leaving the park. So let's look at part D here. Part D says, at what time does a model predict that the number of people in the park is at a maximum? So let me just kind of walk us through the day in the life of the park in terms of just in general, assuming that there's no special event going on. At the beginning of day, which is higher, E of t or L of t?
EFT.
E of t, right? There's people coming into the park. There's probably not many people leaving the park at 10 a.m. in the morning, right? At what point is L of t going to begin to take over E of t? Yeah, probably like maybe early to late afternoon, right? Because E of t is going to start high, L of t is going to start low, but eventually by the end of the day, E of t is going to be it's going to be at the bottom, and L of t is going to be much higher, right? People are leaving the park. Not many people are going to be coming in the park at 5 p.m. or 6 p.m. So the maximum is going to occur when E of t and L of t are the what? Equal, right? Because E of t is dropping, L of t is rising, but when they meet in the middle, that is when the maximum number of people is going to be at the park, because after that, it's going to start decreasing, right? L of t is going to overtake E of t. So the idea is that if we can figure out where H prime is equal to 0, basically where E of t and L of t are the same, then we know that's where the maximum number of people is going to occur, right? So
It's finding critical point.
yeah, basically we're finding a critical point, right? So number of people at a maximum when H prime of t is equal to 0. Right? So I can say 0 is equal to E of t minus L of t. So an easy way for us to, we can obviously set these equal to each other and then solve the equation, but maybe another way to do this is we know that H prime is equal to E of t minus L of t. If I set H prime equal to 0, what if I do this? What if I just graph this and then look for the what? Yeah, look for the x-intercept. I think that's the most efficient way to make the calculator get to what we want to do. So I'm going to go to y equals. I'm going to create a new graph. I'm going to say y1 minus y2. And as I do that, I'm also going to unhighlight y1 and y2 because I don't want to see all these graphs in front of me. I just care to see y1 minus y2. Now, the issue is that when you graph this, you're not going to be able to see much curve because these are all the way up in the thousands. So we're basically zoomed in. And if you graph it, it'll look like a vertical line, right? And it's just harder to trace the graph when you have a vertical line in front of you. So what you want to do is you want to adjust our window so that our Ymin and Ymax can be closer to, see that all these are in the thousands here. So why don't we just go from, we're just choose here, negative 1,000 to 1,000 maybe. And this is a chance for you to kind of just play around and just getting comfortable with your numbers here. And also Xmin, Xmax, we know that we're looking at between 9 and 23, right? So what if I just go from 0 to, I don't know, 30? So I can kind of see around my edges here. So I'm just adjusting my windows here to values that I just want to I want to be able to see the curve for the graph, and I just want to see where across the x-axis, but I want to make sure that I'm in the thousands since my graph is going to have all these high y-intercepts. Right. Let's just see what that gives me. Okay, that gives me a pretty easy graph for me to trace. I can just do second trace 0 and look for that x-intercept. I'm looking for somewhere in that 2 to 3 p.m. range, right? You're probably going to expect the maximum number of people in the park to be in that early afternoon range. So I'll do second trace 0, second trace 0, pick a point to the left of the x-intercept, pick a point to the right of the x-intercept, hit enter. So 15.794, that's around 3 p.m., right? 3-ish p.m. here. So T equals 15.794 is the time when the maximum number of people is in the park for that day.
I have to also check if the signs change, right?
Yep, that's right. And also, yep, the sign changes because we have the graph crossing the x-axis. Yep. Okay. Questions there? Okay, let's skip number 2 for now. Number 3 is really where a lot of these problems are going to look like. And 1's a good example, but I think 3 is really where we can have all the pieces put together here. Okay, so number 3, this is on page 3 here. The tide removes sand from Sandy Point Beach at a rate modeled by the function r given by r of t. Again, we always want to make sure that we're in radian mode, especially when there's trig involved, never in degree mode. A pumping station adds sand to the beach at a rate modeled by the function s given by s of t. Both r of t and s of t have units of cubic yards per hour and is measured in hours between 0 and 6 hours. At time t equals 0, the beach contains 2,500 cubic yards of sand. So there's 3 things that we have to kind of keep track of eventually, that there's sand on the beach to begin with. The tide is removing sand from the beach. And then there's a pumping station that's trying to add sand back onto the beach. So we have to take note of those 3 things there. But part A starts off a little bit easier here. How much sand will the tide remove from the beach during the 6-hour period? Right, so usually part A is kind of getting your feet wet, kind of getting you into the problem before it introduces all the other parts. So the only function that we have to rely on for part A is what?
R of t.
R of t, right? We just care about the what the tide is doing, removing sand from the beach. The pumping station is not going to be in play yet. So what can we do then? We know that R of t is in terms of cubic yards per hour. We want the total amount of sand, so we got to involve what? Integral, yeah. So you know that the cubic yards per hour is going to rise up to cubic yards, which is the unit that we want because we want the amount of sand.
Yeah, 2,500.
No, we don't, because it's only asking about how much sand is removed. It's not asking about how much sand is on the beach. But we will take note of that 2,500 in part B. So that's right. 2,500 is not going to play a role for part A. Okay, so I'm going to so I'm going to save y1 through y3 for the next period. So under y4, I'm going to enter in my function 2 plus sine . Again, use x as your variable. Okay, so oops. $31.816 or 815. It doesn't, yeah, you can either keep that third decimal or make that 9, push it to a 6. Either is fine. Okay, any questions with part A? Part B says write an expression for y of t, the total number of cubic yards of sand on the beach at given time t. So this is a really helpful formula that we're going to see in a lot of rate in, rate out problems. I'm going to go ahead and just have us write this out here. This is going to be really helpful for future problems as well. The total amount at any point in time, we always have to involve the initial amount plus the amount added in that time period minus the amount removed. So we're going to see a common theme across a lot of these problems that's going to have these three components where there's going to be some starting amount, there's some integral that's going to tell you how much can be added to that amount, and then how much is being removed. So we can adjust this general equation for the amount of sand on the beach at any moment in time. We know that the amount of sand on any moment in time is going to have to include that 2,500 to begin with.
This is like total distance.
Is it like total distance? Not really, because total distance doesn't really have that these two components here. But I guess there is that where it's like final position equals initial plus displacement a little bit. So I guess this is kind of like displacement. Okay, but I'm going to write it this way here. I'm going to say the integral from 0 to t of s of x. So I'm just having to adjust a different variable here. I want to give it that flexibility where I can figure out the amount of sand at any moment in time, whether it's 2 hours or 3 hours or 5 hours or 2.6 hours. But I know it's s of t initially, but when the integral gets resolved, the t will get inserted into the function. So we should make sure that if there is an integral with variables in your bounds, make sure that you just start off by using a different variable, right? So that the t can be inserted into the x minus the amount that's being removed in that time period. So now that we have our general equation, we can adapt it to any moment that we want, right? Either it's 4 hours or 6 hours. Okay. But does this equation make sense? Okay, so we have an expression here. We're not asked to do anything with it yet, but this is kind of a starting point that we can use for part C and D. For part C, it says find the rate at which the total amount of sand is changing at time t equals 4. So we want to find the rate at which the total amount of sand is changing, which means that we're looking for what? Y prime. So let's build an equation for y prime, and then we can work in the 4 once we get that derivative. So y becomes y prime. 2500 becomes what? 0. The derivative this becomes what? S of t, good. You don't have to go through this step here. I just want to show you that the derivative and integral is wiping each other out through second theorem. So really y prime of t is back to just S of t minus, sorry, r. Right. We know the derivative of these two notations will drag it back down to S of t and r of t. Now we can finish off part C, right? If I want to find the rate at which the sand is changing, the amount of sand is changing on the beach at 4 hours in, I can just do S of 4 minus R of 4. Okay, so I'll enter in S of 4 into one of my y equations. So I have my S of t stored under y5. I have my R of t stored under y4. I just subtracted that, get negative 1.908. What does that tell us? Yeah, the amount of sand on the beach is decreasing by this amount at the 4th hour, right? Oh, sorry, yes, cubic yards per hour, thanks. Okay, part D. Between 0 and 6 hours, well, what time is the amount of sand on the beach a minimum? Okay. What is this asking us to apply here? Minimum, we're looking for absolute max, absolute min. What does that remind you of? Right? What theorem though? EBT, remember that? So a lot of times these rate in, rate out problems are just going to, that's a common theme, finding max and min. So if I want to find absolute max, absolute min, and I want to think in terms of extreme value theorem, what do we have to consider here? So critical points, we got to find critical points and then points. Yeah. So you don't have to state like in so many words, but you just have to make sure you show that you are applying extreme value theorem, that we want to test the endpoints. We want to test obviously you don't have to test the relative max, just have to test the relative min and then critical points.
You have to like see if it's continuous or something like that, those conditions.
We don't have to worry about justifying it. Yeah, just have to make sure you apply your candidates. Okay. Okay, so if I want to find critical points, that's when y prime is equal to what? 0. So similar to that last problem, we're going to look to see where S of t minus R of t is equal to 0. We can graph this function. And look for the x-intercept. here for my window, I'm gonna adjust it back to between 0 and 6 because I know that it's got to be between 0 and 6 since that's my domain. And I don't have to adjust my Y min, Y max doesn't have to be as large as before. Maybe I'll just go from, I'm just choosing some random values here. I went from -30 to 30. Maybe that's a little bit too large there. Let me go from -10 to 10 for my Y min, Y max. Oops. Or -5 to 5, maybe that's better. Okay, so there it is. I see my x-intercept there. I'm going to use my second trace 0 to get the best approximation possible. So second trace 0. Pick a point to the left of the x-intercept, hit enter. Pick a point to the right of the x-intercept, hit enter. And then hit enter a third time, and it's going to find that x-intercept for you, 5.117. So there's only one critical point to test. So we'll find the amount of sand at 0 hours. We'll find the amount of sand at 5.117 hours. We'll find the amount of sand at 6 hours, and we'll compare them, right? We know that amongst these three candidates, whatever is lowest is going to be will have to be your absolute minimum. And we have the equation built from part B, so we just enter T into the appropriate intervals, right? We can find out. We know y of 0, that's easy, 2,500. Y of 5, we can just enter in 5.117 in for T here, find out the amount of sand added, find out the amount removed, added 2,500, and get that amount. And we'll do the same thing for 6. And so that's the rhythm of these rate in, rate out problems, where you create an equation that has initial amount added, amount removed. A lot of times you're asked to set that equal to 0, graph it, find that critical point, and then extreme value theorem to find the max or min. So I think after we do a couple of these, it's just going to hopefully become second nature and just going to have an idea of how the problem is going to, where the problem is headed. So I just want to introduce these problems to you. We will revisit these after we get through the first quiz. So right now I'm not going to make these other problems homework yet, but eventually these will be homework, and the homework will count towards your quiz grade for your FRQs. So right now I'm thinking let it be 30% of your quiz grade. So so I do need you not starting this day, but starting on Thursday, your homework basically be worth 10 points towards your quiz grade. So if you just show me your homework that's complete on the day of, then you'll earn that 10 points. But at worst, if you show it to me late, I'll still give you 9 out of 10 points. So, you know, if all your homework is late, it's still going to be an A, but why not just get it all in time and earn the full points? So, but tonight, I just want you to focus on preparing for your quiz, and then we'll do the next set of FRQs that we're really going to practice with. But I just want to get you an idea what these problems are, and we'll revisit this once we get past the first quiz. Okay, all right, come get your phones.
So what's the homework for this? Sorry.
Okay, so the homework for this is not gonna show up until this day. So we'll do homework for these three. Starting on page.
I was like, why are we doing?
Page enough, but
So it's the reason.
it's the review, right? So everything's only from the packet. But there's not gonna be any homework Wednesday night. Thursday, I'll tell you exactly what I'm doing for the Friday, so we know.
Okay, but the class problems are.
Right, right.
Christine, I have a question. So if you have like y equals and then you have the equation there, is there a way to just like if I'm looking for increments, is there like plug in for that equation?
Yes, yeah, you can do that. So you want to do the Mars, or you can how about this? You can do alpha trace, line one. So you want to plug in 5. Figure out what that was.
Not bad.
Decimal value, change it to.
Okay.
But yeah, just alpha trace 1 1 and put it parentheses around.
So it's pretty good.
Let's do
Oh, I. Got it. I was like.